great majority of the Earth's physical resources are extracted from the topmost few kilometers of the continental crust. 99% of the Earth's crust consists of just 9 chemical elements: oxygen, silicon, aluminium, iron, calcium, magnesium, sodium, potassium, and titanium. There are more than 80 other naturally occurring chemical elements, and altogether they amount to barely 1% of the crust by weight. And they include many of the metals and non-metals upon which modern industry depends. They occur mainly as trace elements distributed through common rocks. One of the commonest igneous rocks of the continental crust is the plutonic rock granite. The granite that's being broken up here is not being extracted for any particular element. It's just the bulk physical properties of the rock that make it valuable. This quarry is near Shap in Cumbria. Most of the production is used for aggregate. The rock is crushed and then screened, either for road chippings or for aggregate in a variety of concrete products. A small percentage of the granite is cut and polished for ornamental stone. The Shap granite's a distinctive rock. You can see it used as a facing stone on buildings all over Britain. The large pink feldspar crystals are set in a coarsely crystalline ground mass in which you can see white feldspar, glassy grey quartz and shiny black biotite mica. The chemical composition of this rock isn't a lot different from that of the continental crust. Just 9 chemical elements make up around 99% of the total. The remaining 1% or so is mostly trace elements, and they include a number of industrially important metals. But the concentration, the grade of a rock like this is far too low for extraction and processing to be an economic proposition. And that applies to the great majority of common rocks. And it's why this rock is quarried only for its bulk physical properties. But the processes of the rock cycle which form common rocks can also act to concentrate useful chemical elements up to economic grades. Now, a useful starting point for looking at the rock cycle is granite itself. Granites are plutonic, intrusive, igneous rocks. They're emplaced within the crust at high temperatures and pressures, and they only reach the surface long after they've cooled, or when the overlying rocks have been removed by erosion. Now, at the granite quarry, you can see a number of vertical cracks in the rock. They're called joints. They probably formed mainly after the granite cooled and contracted. Along this joint, the granite looks different. It's been chemically altered. The overall reddish color is due mainly to finely disseminated iron oxides. And the rock crumbles rather easily here. It's more quickly broken down by weathering than the granite away from the joints. Now, when the granite's quarried here, it breaks along the joints. And so there are plenty of joint planes to be seen all over the quarry. And virtually every single one of those joint planes shows some signs of chemical change. One of the commonest signs is greenish patches due to the mineral chlorite, which is related to the mica. And another one is crystals of the iron sulfide pyrite. Now, these effects and others are all related to the joints. In fact, they're virtually confined to them. So they must have occurred after the joints formed. And in outline, what happened was this. When the granite was virtually solid, but still at several hundred degrees centigrade, fluids moved along the joints. And those fluids consisted mainly of water. They were very hot and they were very reactive. And they altered the granite on either side of the joints to varying extents as they moved along. They also dissolved a variety of elements, including trace elements, out of the rock. And later on, as the fluids cooled, they precipitated some of those elements on joint planes as new minerals. Here at Shap, these processes didn't lead to the concentration of elements in sufficient quantities to form an ore deposit. But there are many places where ore deposits were formed by the precipitation of chemical elements from hot watery fluids that circulated through cooling granites and through the rocks into which they were emplaced. This is a small tungsten mine at Carrick Fell, about 20 kilometers north of Shap. The ore is in this vein of white quartz, a meter or so thick. It occupies a major joint fracture in a 400 million year old granite, and it extends into the rock surrounding it. Quartz makes up nearly 99% of the vein, but the vein also contains about 1% of the tungsten minerals, wolfram and scheelite. There are other minerals in the vein, including arsenopyrite, but the amounts of these are too small to be economic. The 1% or so of tungsten minerals in this vein may seem a low grade, but it represents a concentration factor of more than 1,000 times over the average abundance in the Earth's crust. So here, there's been a considerable concentration of chemical elements by igneous processes. And those processes happened at depth within the crust. Now, when intrusive igneous rocks eventually become exposed at the surface by uplift and by erosion of the overlying rocks, they themselves will become subject to weathering and erosion. Now, this handsome block of granite was taken from well down in the quarry, well below the zone of weathering. So it's still fresh and hard, and it's tough. But this rather less prepossessing looking specimen is a piece of weathered granite. The feldspars and micas are being decomposed to clay minerals. And of the main minerals, only quartz is chemically resistant. Now, the products of weathering are carried away mainly by water, and they're mostly quartz and clay minerals. And eventually they'll accumulate to form sediments. So the main sedimentary rocks are sandstones and shales or mudstones. This soft and friable rock is a mudstone. It's made up mostly of clay minerals. Mudstones like this one have been used to make bricks here at Whitehaven in Cumbria. This rock is quite different, much harder, better cemented. It's a quartz sandstone. It's not a very pure quartz sandstone, and it does break rather easily along the bedding planes. But sandstones like this are good enough to be used for building stones. Mind you, in some places you do get quartz sandstone so pure that they can be used for making glass. So even in these two very common sedimentary rocks, there's been some separation and concentration of elements. And between these two layers, there's another example of element concentration. Coal. Coal seams can contain up to 95% of carbon. Although, mind you, in this coal, there's nothing like so much. And this seam is rather a thin one. But only a few hundred meters beneath me, there are thicker seams of better quality which are being mined at the present time. And in some parts of the world, you can find coal seams that are many, many meters thick. And where they occur near the surface, they can be mined very easily and economically. Coal-forming swamps are rare on Earth today. This is the Okefenokee swamp in the USA. Here, biological processes help to concentrate carbon in the rock cycle. In the coal itself, There's not many traces of the original vegetation, and that's because the vegetation has been so compressed and it's been subjected to a variety of biochemical and chemical reactions. There's evidence of other chemical processes here too. These thin and irregular layers are ironstone, mainly iron carbonate. As the sediments were compressed and compacted, water was squeezed out of them. The water moved through the sediments, dissolving iron that was dispersed within them, and that iron was subsequently precipitated in concentrated form as iron carbonate, forming thin layers and nodules parallel to the bedding. In some of Britain's coalfields, ironstones like these are much thicker and more extensive, and they were a valuable source of iron ore during the Industrial Revolution. Now, resources that occur in layers that are more or less horizontal present, in principle, a fairly easy problem in respect of mining. You just follow the layers along and dig them out. But in practice, it's not quite so easy. For instance, if we follow this coal seam along, it grades into black shale. The layers aren't continuous. They can thin out or lens out, or they can grade into other rocks. And when you've got resources in this sort of setting, it's a good idea to know the conditions under which they were deposited, so that maybe you get a better chance of being able to predict the direction in which the layers are likely to get thinner or thicker. But there's another and rather more abrupt way of breaking the continuity of layers, and that's by faulting. The relative displacement on this fault is down to the left by at least 3 or 4 meters. That's more than enough to halt production in a modern coal mine. The sediments in these cliffs were deposited more than 300 million years ago. Now they're exposed to weathering and erosion. They're being broken down for further redistribution within the rock cycle. On this beach, there's a magnificent example of sediment sorting and concentration that's happening right now at the present time. Coal is light. Its density isn't much greater than that of water, and so the coal fragments tend to accumulate, to concentrate along the high water mark. This is sea coal, and people have been making a living for years collecting it and selling it. Now here we've been looking at the fragmental products, the solid products of rock weathering and erosion, but there are the soluble products of weathering as well. And they get carried away in solution, and eventually they end up in the sea. And sooner or later, they will also be deposited as sediments. A couple of 100 million years ago, the evaporation of seawater under very hot climatic conditions produced a considerable concentration of chemical elements. This is nearly pure calcium sulfate. It's the hydrated form of calcium sulfate, gypsum. Gypsum is a very soft mineral. But what they're actually mining here is this. And this is anhydrite, the anhydrous form of calcium sulfate. Anhydrite is generally a bit darker than gypsum, and I can't scratch it with my fingernail. Anhydrite is harder than gypsum, and it's also denser. Now, either of these two forms of calcium sulfate, anhydrite or gypsum, can be precipitated as evaporite minerals depending on the conditions. And in fact, this was all once anhydrite, but now exposed at the surface under temperate climatic conditions, especially rainfall, it's being hydrated. It's being transformed from anhydrite into gypsum. Now the dip here is gently in that direction to the east. So this bed gets deeper underground in that direction. And there it's better protected from surface waters. And so it's still mostly anhydrite. And that's what's being mined here. Now nearby, there's another underground mine, and that one is working gypsum. This is the Kirby Thorpe gypsum mine, not far from Penrith in northern England. Gypsum is mined here for the construction industry. About half of the production goes for cement making, the rest goes into plaster and plasterboard. The average grade of the rock here is about 70% gypsum. The purest gypsum is the white fibrous mineral called satin spar. The grey layers in between are mostly gypsum also, but some clay material is mixed with it. This whole deposit was originally anhydrite, in fact. But groundwaters gained access to these layers and hydrated the sulfate to gypsum. Mining is by the pillar and stall method. The extraction areas, the stalls, are arched down to the supporting pillars to minimize the risk of roof falls. The rock is soft and breaks easily, so all that's needed is to drill a few shot holes for blasting with low explosive. After blasting, the broken rock is simply scooped up for delivery to the underground crusher. The rock requires a minimum of crushing before leaving the mine. At the processing plant, it's simply ground to powder and it's then virtually ready for use. So the natural evaporation of seawater is one way in which chemical elements can become concentrated in the sedimentary part of the rock cycle. But by far the best known natural chemical precipitate from seawater is limestone. Lots of limestones have fossils in them, the remains of marine organisms which use calcium carbonate to build their shells and skeletons. This one's a coral. And this limestone is made up mostly of minute spheres of chemically precipitated calcium carbonate. Limestones crop out over much of Britain, being exploited today for a variety of uses. Gorges and caves form in limestones as the rocks are dissolved away by rain and groundwater. The voids created by solution lead to another important step in element concentration. This is the Egremont hematite mine in Cumbria. Hematite is ferric iron oxide, and this is nearly pure hematite. There's over 60% of iron in this ore, and that's more than 10 times the average concentration of iron in the Earth's crust. Here you can see some beautiful crystals of hematite in cavities like this. And in places, the ore's got a banded or a kidney texture. Now, above me here is limestone, massive, compact limestone. And the bedding in that limestone is pretty well horizontal. And the contact between the limestone and the hematite runs through exactly there. It's a sharp contact, and again, it's nearly horizontal, nearly parallel with the bedding. Now, all of this is solid hematite, and it goes on down below me. The top boundary we can see here, and I can show you the bottom boundary over there. This is all solid hematite here, and here it is again. And this is limestone. So this is the bottom of the hematite body. And the boundary is a sharp one, and it's not very far off horizontal, gently inclined in that direction, which is not very far off the bedding of the limestone. It's difficult to see here, but that's inclined gently in that direction as well. Now, what's happened here is that a large mass of limestone has been dissolved away and replaced with hematite. And that replacement has happened more or less parallel with the bedding. Now, just here, the geological relationships are reasonably easy to see, but this is only a very small part of the mine. By careful mapping of the labyrinth of old workings, it's possible to show that the ore bodies are associated with faults. But they are irregular in shape, and the true nature of the mineralization is still uncertain. The relationship between mineralization and limestones is much clearer here, at the Silver Band mine near Appleby. The mineralization is in near vertical veins, cutting through horizontal beds of limestones and shales. For many centuries, these veins were worked for the lead sulfide galena. But now it's this mineral, barium sulfate, barite, that is in demand for use in oil well drilling. The mineral veins fill fractures in the limestone, which have been widened by solution. But the mineralizing fluids were stopped at the impermeable and relatively insoluble shales above. So the mineralization is confined to the limestone. Those last two examples of element concentration, that's the replacement of limestone by hematite at Egremont and by galena and barite at the Silver Band mine, they obviously occurred within the sedimentary part of the rock cycle. Equally obviously, the ore minerals were introduced long after the sediments had been compacted and consolidated. Now let's move a little further on along round the rock cycle. Where sediments accumulate and are buried to great depths, especially at continental margins, they can be subjected to enormous pressures and temperatures. They become metamorphic rocks. This is slate being cut from a hillside at Burlington in the west of the Lake District. Once these were soft muds deposited in an ancient ocean. Burial has resulted in a hard rock with a new layering, slaty cleavage. The planes of cleavage enable the rock to be split to make the familiar roofing slate. The pressures caused by the burial of the original muddy sediments produce recrystallization and an alignment of minute mica crystals to give this useful slaty cleavage. Now, with higher pressures and temperatures of metamorphism, recrystallization produces coarser-grained rocks. This mica-rich rock with lots of little folds in it is a schist. And these rather roughly banded rocks are both gneisses. Now, metamorphism involves a redistribution of chemical elements to make new minerals. There's a lovely example here, deep red-brown garnet crystals in this gneiss. Now, this gneiss is made up largely of feldspar and quartz and mica. Its composition isn't very different from that of granite. And it's not difficult to see that if the temperature were to rise a bit more during metamorphism, a rock like this could begin to melt, and so bring us back round to, in the rock cycle, to where we began, with granite.